So welcome again, everybody. Good afternoon. Well, this is the season finale, the series finale, more like, and well, let's let's dive right into it, right? Let me just share this screen. All right. Okay. So here we go. Let's do this, right? So welcome back. I hope you had time to digest a little bit of what we saw in yesterday's lecture. I had a plan for today's lecture, but after yesterday's lecture, I was a little bit I was not sure that all the concepts that we talked about really really sunk in, but I guess, well, the first contact of anybody with this kind of subject is always very tricky. It took me a while to get the hang of it, but even though I said all that, I wanted to talk to you about it again. I wanted to retrace our steps in more detail than only a that only just a previously as we did in the other lectures. I want to retrace our steps and maybe take a different path, not so different, but a little bit more what I think it might be a little more friendly, okay? A little bit less intimidating, which is the point, right, of this mini course is um to make it more palatable, okay? So let's do this. So recall that we saw all this, right? We saw the spherical tensors and its orthogonality relations, right? We saw how to take the inner product of these objects in the two-sphere, right? Which involved taking the integral of the multiplication of the complex conjugate of the object with itself and integrating in the two-sphere, right? But I think this kind of approach, maybe it can be a little intimidating, right? It may seem like something that we don't always do, right? But in fact, we do all the time, right? When we have an arbitrary vector, an arbitrary object, and we want to see the component of that object in the direction of some of the basis vectors, right? What we do is project. And to project, we mean taking the inner product of the object with one of the basis vectors, right? And since we are working with a basis, which means that the elements of this basis are linearly independent from each other, what we'll have left is the component in the direction of that vector in which we took the inner product, right? And it's exactly what we are doing here, right? When to separate the radial part and angular parts, all we did was to construct a basis, right? We constructed a basis for the angular part, which contained scalars, vectors, and tensors, right? By the way, this is the corrected version, okay? I asked Nicholas to submit some corrected versions of previous lectures because as I was correcting the slides, I found more errors. So, and I found out that the book by Valeria had other errors as well. But don't hold it against it. It still is a great reference, right? But since it's a first edition, subsequent editions will, for sure, they will correct them, right? But these little errors sometimes causes a little trouble. But it also grants you an opportunity to do the calculations by yourself, right? To reproduce this and and find these errors, right? But okay, so that's what we did, right? What we did was we constructed a basis for the angular part, right? And what we did to separate was to create by moving and multiplying by some multiplication and summations to construct a orthogonality relation, right? But I don't know. For me, it was confusing when I saw that the first time. I didn't really understand what was going on. So I tried to come up with a way to show you what is happening. And of course, it is I will be hiding all the mathematical structure that is behind what is going on, which is this, right? I will need to hide them, right, into a more friendly, friendly looking setup, right? But since you already know what is going on, maybe um, with this new approach, it can be it can be more easy to absorb, right? Which is the main goal here, right? Which is my purpose. So if we look at all this in another way, in fact, it's not another way, but I mean, from a different angle, maybe. So the spherical tensors can be represented in such a way, okay? The vectors, right? The scalar will be the spherical harmonic, as we already know and love from quantum mechanics, the YLM, right? But here we are constructing the vector basis, right? So this is the vector, the tensor, the spherical tensor, which is a vector, a 0, 1 tensor, and it is even, the even vector. And this is the odd vector, right? And what we mean by the orthogonality relations is basically this, right? So to take the inner product, when we're dealing with tensors and tensor notation, to take the inner product means that we are contracting the vectors, right, with the metric. And since these vectors, they are only vectors in the two-sphere, it makes sense that we take the inner product with respect to the two-sphere metric, right? So you see here that when we take the inner product of a vector with itself, it will yield not one as we would expect, but this quantity here, right? Okay, so when we do, so which is basically analogous, right? It's just it's not normalized. This inner product is not normalized. Okay. But okay, so the same happens here when we take the inner product of the even vector with itself, right? The same happens. But when we take the inner product of the even vector with the odd vector, it goes to 0, right? You can actually prove this, right? I tried it myself yesterday as I was preparing the alterations to this lecture. You can prove that if you take the inner product, right, in this manner with the integral and the complex conjugate and so on and so forth, if you take the inner product of YA with SA, it will yield 0, right? So basically, what is happening is completely analogous to what we did, what we have been doing for ages, right? In vector calculus, right? You take the inner product of two basis vectors that are linearly independent of each other, then this will happen, right? The inner product of one vector with itself will yield a vector a value different than 0, right? If it's normalized, will yield 1, right? And if you take the inner product of two different basis vectors that are linearly independent of each other, the inner product will render 0, right? And the same can in analogous form can happen. We can arrange for the tensors, right? So if you take the inner product of a tensor of another with another tensor, which basically means a contraction using applying the metric 2 times, right? One for each pair of indices, okay? So the inner product, so here we defined a even tensor, right? And the odd tensor, okay? This is the exact same way we did here, okay? This, I'm only translating this, right? I hope that this is clear. Okay, so I hope that is clear that all that I'm doing is translate this into a more friendly form, right? So YA is basically the EAE, right? The even vector, and the SA will be the odd vector. And the same goes here. This would be ZAB, right? And this would be SAB, right? Which we are already acquainted with. Okay, so then when you take the inner product of the odd tensor with itself, it will render something different than zero, right? The same goes if you take the inner product of the even tensor with itself. But when you take the inner product of the even tensor with the odd tensor, it will render zero since they are linearly independent of each other, right? There are two basis elements of the there are two basis elements which construct a basis for all 0, 2 symmetric and traceless tensors, right? Okay. Is there any questions here? So is it clear what is happening here? Is there any questions about this is only a translation. I'm only doing this because I think this way here is a little bit very intimidating, maybe. This I think is a little more friendly, right? So is there any questions about this? Are there, right? Any questions about this? Okay, I will assume we don't have any questions about this, so I will continue. So, okay, so the decomposition, the harmonic decomposition for fixed L and M, which I mean by that is that I won't be taking the sum over all L and all M. I'm taking only fixed values of L and M, right? To obtain the full answer, you have to sum over all L and M, right? But we won't worry about that, okay? So the harmonic decomposition, we already saw how the perturbation decomposes in the harmonic way, right? So what I mean by that is that there's a angular part, there's a complete angular part, which is here, a mixed part, a complete not angular part, right? Which depends of T and R at first, right? So this would be in this new notation that we are using, the harmonic decomposition, right? So I maintained the spherical tensor, the scalar spherical harmonic as the basis for the scalars in the two sphere, okay? But I changed the notation for the vectors and tensors, right? So here is the decomposition, right? So you see, this is the same, this in particular is this exactly the same as a component in the direction of this basis vector. And this could be seen in the two sphere at least. As far as the two spheres is concerned, this is a component, right? This is a scalar. So this would be the component in the direction of this vector. And this would be the component in the direction of this vector here, right? This is only a tensor with respect to T and R, not with respect to theta and phi, right? Okay, and the same goes here, right? This is a 0 to tensor with respect to the two sphere, right? Which is built in this way, right? This is a tensor. We constructed a tensor basis, right? Which makes any perfect sense since the multiplication by scalars a tensor multiplied by a scalar is another tensor, and the sum of two tensors gives us another tensor, right? So this is exactly what is happening here. This tensor here is constructed as such, right? With this basis and this basis and this basis, and these are the components of this basis, right? Okay. So then we can also decompose our metric perturbation with respect to parity, right? The same way we did. Oh, I see that someone raised a hand here. So I'm gonna stop. Is there any questions?
Yeah, can you hear me?
Mm-hmm.
Hello? Yeah, so my question is, yeah, we are doing this decomposition of the four manifold into this TR and theta phi. But
Mm-hmm.
what is the motivation behind doing this decomposition? Of course, we are seeing that there are scalars and tensors and this spherical symmetry and stuff, but what is the motivation? Yes, I mean all the
Okay.
mathematical things are clear that these are symmetric, orthogonal, and this normalization relations. But
Mm-hmm.
why decompose the four manifold into a M2 into a cross S2?
Okay. Great question. So, the thing is, our problem is a spherically symmetric problem, right? So what I mean by that is that the perturbation itself will be spherically symmetric in a sense that what we have to look really are the components, the metric perturbations. Uh, in this decomposition, we see that the metric perturbations here, the functions that are related to the metric perturbations, they are written in a basis that is spherically symmetric, right? So the motivation is the symmetry of the background metric. So we are doing perturbation in Schwarzschild space-time, which is the exterior solution to a spherically symmetric object. So all we are saying, so to do this decomposition helps us because now we don't have to focus on the angular parts, right? Because we constructed the perturbation in a way that we can separate the angular part because there is a spherical symmetry, right? So spherical symmetry basically means that that the problem is invariant under rotations, right? So this means that the same way as we do the Fourier transform, because the metric is static. What I mean by that, the Schwarzschild metric does not depend on time. It has a invariance. If you look at the metric at an instant t, and you look at some later t1, t2, a moment later, the metric will be exactly the same. This is why we can model our perturbation, our age, into a part which is the time dependence in e to the minus omega t, and a part which is only radial, right? This separation, this ansatz, you are only allowed to do that when you have a symmetry, right? When you have a symmetry, or in this case, when we have a spherical symmetry, right? Otherwise, we wouldn't know how the angular part and the radial parts are related to each other, right? They could influence one another. There could be a non-linear relation, right? So it's basically the same as when in electromagnetism, when we do the separation, the separation technique to solve differential equations, right? So when we have our wave, our electromagnetic wave, and we describe it as an r, and the function r times the function t, right? And then we take the full derivative, the partial derivatives, and so on, and we transform what was a partial equation, or a partial differential equation, into two ordinary differential equations, right? So this is what we are doing this, right? But this demands a symmetry. So the symmetry is provided by us by the background metric, right? The Schwarzschild metric is spherically symmetric. So what we are using this in our favor, right? And the way to do so is to use as basis objects that are invariant under rotation, which are these objects here, right? But since we have a priori a a dependence, right? We have a function that is dependent of t, r, theta, and phi. To do this separation, we use the basis of the manifold S2. This is why we separate them, right? So we can use this spherical tensors as basis, so we can separate them easily later. Does this answer the question?
Yes, thank you.
Okay, so let's proceed. Great question. Uh, I thought I said more about this in previous lectures, but even if I had said something about it, is always good to repeat it. Okay, so let's proceed. So then we can also do the decomposition of the metric perturbation with respect to parity relations, right? The same way as we did the basis vectors, right? The basis vectors and basis tensors, right? So we can separate into an even part and an odd part. And this would be it, right? This would be the even metric perturbation and the odd metric perturbation, okay? So you see that all that we done before is also valid here. These are all even functions, right? And these are all odd functions, which I hope that is more clear to see that, because now we have indices that we have a notation that indicates this more evidently, more explicitly, right? So okay. So here is how we construct this, right? In the Reggie-Wheeler gauge, so remember, the Reggie-Wheeler gauge, we set this function, or I mean the components of the even vector are zero. The components of the even tensor are also zero, and the components of the odd tensor are also zero, right? So all we have left in the odd perturbation are the components of the odd vector, right? And here what we have left, it's only this element here and this element here, right? Which is the trace part, right? The trace part of this. This would be the traceless part, right? So this goes to zero, this goes to zero, this and this survives, right? So let's see how to construct our odd metric perturbation given this, right? So this is a vector with respect to T and R. This is a vector with respect to the two sphere. So this is basically a multiplication of vectors here, right? So this is what we are doing, right? We are taking age A, right? We're taking this vector here, and we are multiplying by this vector here, okay? Which renders this matrix here, right? But this metric, but we need to symmetrize this. What I mean by this is that this and age mu nu and age nu mu must be equal, right? So we have to symmetrize this, which is basically to say that these two components here, these two matrix elements here are equal to this here, right? The 0 theta and theta 0 will be equal, and so on and so forth. Okay? Just as we did earlier, but now I'm showing explicitly how to construct them, okay? So this is what we did. And it was implicit in the previous lecture. So this is the odd perturbation in the Reggie-Wheeler gauge, okay? And also for the even part, let's take a look again. What is left in the Reggie-Wheeler gauge is this element here and this element here, right? So basically, this is a scalar, this is a scalar, this is the metric in the two-sphere, and this is a 2x2 matrix, right, with respect to TNR. So let's see, this is age capital AB, right? And this is the metric with respect to the two-sphere, but now we brought it to our four-dimensional space-time, right? The induced metric is here, right? The metric of the two-sphere is here, right? Which is basically setting all this, just focusing in this this matrix here, this 2x2 matrix. But we brought this matrix to the 4x4 space-time, right? So these are scalars, this is a scalar. So if we sum this, right, since this is exactly what is happening here, if we sum this is what we get, right? This is the even perturbation. And again, this mistake here. I'm so sorry. I will correct them before I send it to you guys later today. So okay. So now for a fixed frequency, right? Because the time dependence of these perturbations are given by an exponential to the minus I omega t, right? So if we fix this one frequency, right? Because this is the Fourier transform gives us an integral, right? A sum over all possible frequencies. But if we focus in each frequency and each value of L and each value of M, in the way that we don't have to put all those summations over L and M, and we don't have to do the integral over the omega. So after we do the Fourier transform, which we can do because the space-time has a time symmetry, right? This is why we can do this. So we can separate our age mu nu into a radial part times time part, right? So after the Fourier transform, and obviously, after we apply, so if we put this together, right? We put this metric perturbation together with this, right? We sum them again, we sum them back in this, right? We saw who this is and who this is. Then we sum them and put them together. So we sum this matrix with this matrix here, and then we have the full perturbation. And then if we apply this perturbation into the expressions for the Ricci tensor, the Ricci scalar, and we put them all together in the Einstein tensor, right? And we take the covariant, the first and second covariant derivatives, and we turn all that machinery. What happens is that we will have the Einstein tensor will be able to be decomposed in this same form, right? Imagine that here we have a delta G mu nu, and here we have a G, capital A, capital B. Here we have a delta G, A, delta G, A, delta G, small caps AB, and so on. So we harmonically decompose the metric, right? So let's look what happens to each of these quadrants, right? Exactly the same way that we did for the Ricci tensor, right? Yesterday, the perturbed Ricci tensor, but now we're doing with the full Einstein tensor, right? So after that, this is the first quadrant, right, of the full delta G mu nu, right? So these are formed with exclusively even functions, right? ALM 0, 1, 2, 0, 1, and 2 are all even functions, right? Since they are multiplying this even basis element. And the same happens with the mixed part and the tensor part, right? Okay, so this is what is happening, right? We saw this exact expressions for the Ricci tensor, right? Which is completely analogous, right? The odd equations at least. So, okay, so this is what we have, right? We have this matrix here times this scalar. Here we have this decomposition, right? This is a vector with respect to the to the two sphere, right? This index here is with respect to TNR, so it doesn't mean anything to the two sphere, right? The only index that matters for the two sphere is this one here. So this, if you look at this, as far as the two sphere is concerned, this is a vector, right? Which can be decomposed in a basis, right? This is the component of this basis, this is component of this basis vector, and so we have a vector, right? And here, this is a tensor with respect to the two sphere and a scalar with respect to TNR, right? The TNR part of the manifold is only concerned with capital indices, right? So as far as the TNR part of the manifold is concerned, this is a scalar, right? And we can see that because, look, this is a scalar, right? This is a scalar, this is a scalar, this for TNR is a scalar, this is also a scalar for TNR. But for the two sphere, this is a tensor, right? So here we have a tensor, which is the two sphere metric. This is the even tensor basis. This is the even basis, the odd basis tensor, right? And these are the components, right? So the decomposition, the harmonic decomposition is exactly this. This is what we did. So, okay, so let's use again that analogy with vector calculus, right? So take a look at this, right? If you want to obtain the components of this basis vector in the direction of this basis vector here, all we need to do is take the inner product of this object here with this vector here, because the inner product of this vector with itself is gonna render the L times L plus 1, but the inner product of this vector with this will render 0, so we get rid of this, right? And then we end up with this components, right? With what we want. We want to know the components in the direction of this basis vector. If you wanted to know this, we do the opposite, right? We take the inner product of this object with respect to this this basis vector. And the same goes for the tensor, right? For the tensor here, if you want to take this basis, these components, we only need to take the inner product of this tensor with this tensor here, right? And to get this, we need to take the inner product of this whole object with this, right? Okay, so, and we know that this is orthogonal to this and this because this is traceless, right? To take the inner product of this tensor with this is the same thing as taking the trace of this vector of this tensor here in here. So okay, and if we wanted to to obtain this components here, all we need to do is take the inner product of this with the metric, which is basically taking the trace, right, of this tensor here. And this would go to 0, and this would go to 0 because it doesn't have any trace, it's traceless, and this is traceless also. And then we would have this only thing left. And then here, the only thing we need to do is to multiply by the complex conjugate of this here. Okay, we would need to integrate in the two sphere, but the thing is, we don't need to, right? To know which of the energy momentum tensors that are corresponded to each equation here, all we need to do is identify them, right? So there is no problem here, okay? So let's do this. Let's obtain the odd equations, right? Which are basically here and here, right? These are even functions. Remember, these are multiplied by an even basis element, right? This is even because multiplied by the even vector. This is even. This is clearly even, and this is odd, and this is odd. So the odd equations will come from here and here, right? So to obtain this, we need to take the inner product of this object with respect to the odd basis vector, right? Such that taking the inner product, right? This is exactly what we did. To take the inner product is the same as to multiply them both and contract with the metric, right? Remember, we are doing with the metric of the two sphere because the indices that we are contracting are small caps, right? So they are only indices, vector indices, right, with respect to the two sphere. Okay. So okay, this is what we did here, and this is the same as we done here. So this is the inner product of these two matrices, right? And this would be and this is the component in the direction of this tensor here, right? Okay, so now we isolated them. We didn't need all that shenanigans of multiply this equation by this and this other equation by such and subtract them, right? We just took the inner product of the whole tensor perturbation, right? With respect to one of the basis vectors that we wanted to obtain the I'm sorry, to obtain the components, and we obtain them, right? Which is exactly the same as we did, right? I'm hiding what the mathematics of what is going on here, right? What is really going on is what we saw in the previous lecture, right? We multiply things by the some objects by the complex conjugate of some objects to construct by hand the orthogonality properties, right? But this is what we need to do only, okay? Okay, and well, the equations are the same. We didn't change anything. And after all, we didn't do nothing different, right? We only changed the notation and the approach, but the mathematics is exactly the same. So the equations are exactly the same as we saw in the previous lecture, right? So here we have first and second derivatives of the odd metric perturbations, right? H0 and H1. Here also and here also, okay? So now, okay, so this all was a prelude to what actually want to talk about today, which are how to get to the master equations, okay? Just to make sure that all is clear, right? Because this is the important point here, right? Because this is a very much less convoluted approach to separating the angular parts, right? At least I think so. I think that it is a little bit less confusing, maybe a little more direct approach, even though we are not exactly showing what is happening mathematically, right? But you get the point. So, is there any questions about this? Is it clear that this is completely analogous to what we did yesterday, and that and I don't know, maybe is this more a little, in fact, more clear than what we did yesterday, or the same? I don't know. If you have any questions, now is the time. Victor, is there anything on the chat that I'm not seeing? Please. I don't know if Victor heard me. Victor, are you there? Well, I'm not sure. Are you all are you all listening? Can you hear me okay?
Yes, yes, yes. Yes, we can hear you.
Oh,
Yes.
okay. Okay, thank you. Okay, so I'm checking the chat here, so I see that there is no further questions. So okay, so let's go. Let's go to the master equations, which is the whole reason why we've done all this, right? Okay, so note that as we talked about in the end of the previous lecture, not all the odd equations are independent, right? You can do some combination of the first derivative of one equation and summing with the other and obtaining the third, right? And it is possible to show that such a combination of the first derivative of beta 1 or t, I don't really remember which, and summing with the other, subtracting yields beta 0, right? So beta 0 is a redundant equation, right? So we can just get rid of it. So what is left for us is these two independent equations, right? This is beta 1, right? And this is t, right? Important note here. Remember that all that goes on the left side must happen also on the right side, right? So all we did here was the same thing as we've done here, right? We prepared our energy momentum tensor, the perturbed energy momentum tensor, the same way as we prepared the metric perturbation, right? So to obtain the correspondent, right? If we equal this to 8 pi to 16 pi delta t a, you would obtain some energy momentum components for the even vector and some components for the odd vector, right? So taking the inner product in both sides, okay, on the left-hand side, we obtain beta, and from the right side, we obtain the correspondent energy momentum tensor, right? Which is exactly how we obtain this, okay? And correspondingly for T, this. Okay, so if we make, so let's go. We're gonna try to turn these two equations into one equation, right? And see what happens. So if we do this, so we set 16 pi delta t1 of the odd perturbation of the odd energy momentum is equal to A, and the other one is equal to B, okay? This is what we get, right? We only relabeled so that we can be easier to track. We don't have a very confusing and very bloated notation, right? So what we're gonna do now is let's isolate H0 here, right? In such a way that we obtain this equation here, right? I'm just isolating this, so subtracting this from both sides and dividing by y omega f inverse, right? And then we obtain this equation here, right? Okay. Now you see that in this equation we have H0, but we also have H0 prime, right? So what we do is, well, we take the first derivative with respect to r of H0, right? Such that we obtain this, right? To do this, we have to apply the product rule and inside the parentheses also, and so on and so forth, right? This is going to be a huge expression, right? So what we're going to do now is substitute H0 right here and H0 prime right here, right? Okay, let's see. Let's see how this ends up looking like. So here I only pointed out the substitution of H0 prime, but there's also the substitution of H0, right? I'm gonna correct this. But yeah, so we need to substitute H0 and H0 prime. So that we have only an equation that only depends on first and second derivatives of H1. That only depends of H1, right? We are getting rid of the dependence on H0. That is all we are doing. So substituting this in all the H0 prime and H0 into here and here, we get this equation here, okay? If you compare this with the references by Berti and by Valeria Ferrari, you're going to see that it's different because in these objects here, when they take the second derivative and first derivative of f, they already assume that f has a specific form of the Schwarzschild metric, right? 1 minus Tm over r, right? But if you do this, if you substitute this by the f by 1 minus 2m over r, and take the second derivative here, and the first derivative here, and regroup everything, you're going to see that it perfectly matches the answers from Valeria Ferrari and from Berti. Okay? So this is the equation we end up so far, right? So I put it on the right-hand side, all the terms that are corresponding to source, okay? So here we have the source of beta 0. Here we have a derivative of f times the source for the t equation. Here is the source of the t equation. And here we have a differential equation, right? Is a second order differential equation for h1, right? Which is linear. Okay, so now we're going to see how to simplify this, right? Because we have this, and basically all we need to do is to solve for h1, and then having the expression for h1, we substitute here, and we have another equation, right, for h0, right? And we solve this one so that we obtain h0, and we have the full odd perturbation, right? But this could look a little bit more friendly, right? So what we're gonna do now is present what we call the Reggie-Wheeler function Q. Okay, the Reggie-Wheeler function QLM is related to H1 in the following manner, right? So H1 is equal to R over F times Q, okay? So if we substitute this into this, so if you take the first derivative and put it here, and the second derivative and put it here, and substitute here, the expression for h1 in terms of q, we end up with this equation, right? Which is a lot more friendly, right? Here in f, what I call f is exactly this function of r here, right? After all the energy momentum tensor components and f are all functions of r, right? So this I put it all into one label, which I call FLMR of r, a function of r. But this way we cannot identify this right away, right? So to clarify what this expression really is, let's introduce a coordinate transformation, right? Our theory is completely invariant under coordinate transformations. So let's do one. And now we're going to present to you the famous and most loved tortoise coordinates. I'm sorry, here. The tortoise coordinates, right? The tortoise coordinates are this R star, and such that the R star is related to R, right? In this, by this expression here, okay? This expression relates R star with R. So here we see that R star is a function of R, right? And then with this, right? If we solve this equation here, if we integrate in both sides, we see how the coordinate R star is related to R, which is basically contains terms of the natural logarithm of f and so on and so forth. Okay, this is a very famous coordinate transformation in general relativity, especially when we are trying to show that that 2r equal to m is not a real singularity, right? that we can easily transpose that region. This is part of the Eddington-Finkelstein coordinates, which is not the perfect coordinate system to see that. The Kruskal coordinates are the right coordinates to see that the region of r equals to m is not singular. But this is part of the path to get to Kruskal, right? If you've seen general relativity, you know what I'm talking about. If you haven't yet, maybe you will in the future. Okay. So now in this coordinate, so if we change these derivatives, right? Change the derivatives with, through this relation, change the derivatives with respect to r, and now take the derivatives with respect to r star, and taking into account that f has this form here, right? Now I'm leaving the general form of the function f, right? And sigma is basically the Schwarzschild radius, right? Which in the Schwarzschild spacetime, this Schwarzschild radius is equal to 2m. And okay, but anyways, through this coordinate transformation and taking into account that f is equal to this, okay, our equation becomes this one. Okay. If we haven't, you may wonder, if we haven't done this, what would happen? Well, you would have a term here, right? You would have a term in derivatives, a derivative in first order of q, right? Here we have a second derivative with respect to r of q, and here we have q. But if we maintain the general form of f, here would be a term which would be the first derivative of q times some combination of first and second derivatives of f, which this form of f equals to 0, right? So the same way that there is a combination of derivatives of f here, we would have another term, and you would be multiplying the first derivative of q with respect to r star, right? But the differential equation with respect to f inside this parentheses that would be here, right? Multiplying the first derivative of q is solved by this function f in this format here, right? Which is basically saying that if we maintain the spherical symmetry of the problem, right? This is the equation we obtain, right? Because this function f, this form of the function f, is precisely directly related to when we solve the Schwarzschild metric, right? With the assumption that we have spherical symmetry, right? So assuming this is the same as to assume that our problem maintains its spherical symmetry, right? So what is the term that is multiplying the first derivative of q, if we maintain the spherical symmetry of the problem, goes to 0, and this is what we have left, right? Still, this is not, if I ask you guys, have you seen this equation before? Maybe many of you will say that haven't, right? Even though you have. So let's relabel some things here so that we can see where I'm going, right? So if we rewrite this equation, we get to this, right? So I turned the term that is multiplying q here into this, okay? And now we have our full equation, right? Does anyone recognizes this equation? You can put in the chat if you want. I want to see if you guys recognize this equation here in this format at least. If anyone recognizes this equation, please comment on the chat. And well, I think you guys are very shy because you do recognize this, right? The only difference, um, more general than that, João. But yeah, the harmonic oscillator is a kind of solution of this, right? Is a specific solution. This is a Schrodinger equation, right? With a source, yeah, yeah. So this is a Schrodinger-like equation, right? If you haven't done I'm sorry, if you haven't done the Fourier transform, we would have not only derivatives with respect to R star, but derivatives with respect to T as well. But the derivatives of Q with respect to T, when we do the Fourier transform, all it does, it drops two terms of omega, which multiply each other and goes to, so the second derivative of Q with respect to time yields this object, it yields this term here, omega squared, right? So this is basically the Schrodinger equation with a source, right? But yeah, your answers are correct. Okay, so just to make sure. After all, the harmonic oscillator solves the equation, right? So it is one possible solution. Uh, so yeah, after all this time, we're wondering, maybe you weren't wondering, right? But maybe you were. What is the analog for the curved space-time in this, at least in the case of Schwarzschild space-time, which is the correspondent to the wave equation that we obtained for the flat space-time, right? This is the correspondent wave equation, right? A Schrodinger-like equation here. Here we have a potential, right, in which this wave will propagate, which is due to the geometry of the background metric, right? If I show you who is the potential, right? This is the potential, okay? You see that this potential is tightly related to the geometry of the problem because these are functions of the background metric, right? So the geometry of our background works as a potential which dictates how this wave will propagate, right? In such a way that if we look at this far away from sources, right? If you go very, very far away from sources, i.e. r equals to infinity, you can check that this goes to zero, right? And what we would have is a free wave, right? A wave propagating freely without a potential, right? This potential will go to zero at infinity, which is basically what we did to obtain the homogeneous wave equation when we did flat spacetime, right? Far away from sources, this would go to zero as well. And basically, this would be the equation, the full equation, right? The second derivative, I'm sorry, in fact, this would not be the full the full equation, right? Would be the second derivative of Q with respect to R star plus omega squared times Q, right? And by solving this, we would have a solution very much analogous to that we obtained in a flat spacetime, right? This is the wave equation, right? Which, yeah, you can see as an oscillator, right? A damped oscillator. So yeah, so okay, this is the function f, right? I substituted here the expressions for a and b, right? Such a way that this is what we end up. This is the source, right? And this, my friends, is the famous Reggie-Wheeler equation. Okay, so this is a wave equation which governs the behavior of the of the odd part of the metric perturbation in short shift space-time. Okay, so the odd part, is concerned of the which is related to the odd perturbation, metric perturbation, is governed by this equation here, right? So we solve for Q, obtaining a equation, a solution for Q is the same as obtaining a solution for H1, right? Since they are related by multiplication by F and R. So if we know the solution for this, we get the solution for H1, and having the solution for H1, we can obtain the solution for H0 by plugging H1 prime and H1 here, solving this differential equation, right? Or more easily, in fact, putting this expression for H1 here and here, right? I'm sorry, I forgot that we have an expression for H0, right? So if we know who H1 is, take the derivative and put it here, take H1 and put it here, and we get who H0 is, and hence we have the full odd perturbation, right? Which is basically this, right? We put it back here with the basis of the angular part, right? And that's it. We have the whole odd perturbation. Okay, so let's retrace our steps once again, right? So we did the projection of the tensors and vectors onto the basis that we wanted to look at the components of, right? Here and here and here. And we obtained the equations. We did the same on the right-hand side and obtained the energy momentum tensor components, right? And then all we needed to do was to, okay, let's try and put these two equations together, right? In such a way that we have a dependence on only one of them, but they are related with each other by one of these equations here, right? And then by doing some relabeling the source and relabeling in substituting equations and so on, we ended up with an equation that only depended on H1 and its derivatives, right? And by presenting the Regge-Wheeler function, right? We came up with a very more friendly equation, but to really see this as a Schrodinger-like equation, we put it in another coordinate system, right? Trading R by R star. And in this coordinate system, we get this equation here and relabeling again, identifying this part here as the potential, as the odd potential, we get to the Regge-Wheeler equation, which is basically a Schrodinger-like equation, right? And here is the source term, right? Is it clear to you guys what this means? The fact that we obtained a Schrodinger-like equation might be of no surprise to any of you, right? Because we needed an analog equation with respect to the one that we obtained from flat space-time, right? We had the wave equation there, right? And now we have a wave equation here. Okay, we found it. We did it. Congratulations to you all. We survived. Okay. The thing is, we need to still look at the other part. Okay, to the even part. So this is the Regge-Wheeler equation. And we're not out completely out of the woods yet, because we have the other part to find out. And this other part is kind of pain in the ass, right? It's very huge computations to do, right? And I thought it would be a complete waste of time doing them all here, because maybe, I don't know, this kind of long computations tend to set people astray, right? People, people I start to lose people here, right? I know that when I attend classes, I know that very long computations and tedious computations may lose my full focus and attention. So what I'm gonna do is, well, basically the path to this really master equation is exactly the same, though much more extensive, which is basically based on, um, well, instead of getting this and this equation, we need to separate this, and all these four equations here, right? So you can imagine how extensive this could be, right? Because now, instead of three equations, which one of them we can throw out, we have 1, 2, 3, 4, 5, 6, 7 equations. Some of them we could throw out, but nevertheless, we would end up with a set of at least four or five equations, if I'm not mistaken, right? And we would have to relate them in such a way as we did here, but here we had only two functions, two unknown functions, and two equations here. So it was very easy to do this fusion, right, of these two equations into one. And it's the same thing that we must do for the Zerilli equation, right? Which would take us forever, right? But to avoid leaving you without seeing how this solution looks like, right? And without having to turn to the references, which would it would not be cool, right? I'm going to show you the computations that I did for my research using my notebook on Sage Math, right? So let's go. Let's go to Sage Math. Let me just do this, and I need um, just give me a second. So that I can do this. I can open. I haven't opened this earlier because I think it would jam my whole computer. So I'm doing this in a more careful way. But as my computer decides to try and work, and have you any questions so far about what we've done? Is there any questions? Let me stop sharing for a moment. Can start sharing later. So no. Wait a second, Victor, because I'm going to show them something from my notebook, which is part of the results. So let me just show them this, and then we can close all things. I mean, I have a final slide also, but anyways, first things first. But thank you, João, and thank you, André. You're right on the money, right? You're right on the money. I answered in a different way, but oh, great question. Great question. This question is so great that I'm not sure how to answer you because this is still something that I'm working on and learning as well. The fact is, as I watched a seminar, I'm oh my God, the name slipped my mind. But I saw a seminar on gravitational waves that model gravitational waves with two polarizations. So I think that somehow, I'm not quite sure, but maybe there is a way to put together these functions, right? H0, H1, and the functions that we obtained from the Zerilli and combine them in such a way to produce two different polarizations, right? But to see that, we would have to solve the Reggie-Wheeler and Zerilli equation. And as you might see in the slide, this is far from a trivial differential equation, right? Um, yes, I think it is. I think it is. I don't remember. He's famous. He's huge in the field. The name just slipped my mind. And it's a seminar that he presents on a lot of universities. He presented here on a colloquium in UFABC, but it wasn't full because the colloquium only was 50 minutes long, and the seminar is a lot longer. But he doesn't. I don't know if he covers that on the seminar. This is my assumption, right? Because if the astronomers are still modeling and modeling constructing their models of gravitational waves with two polarizations, maybe there is a way to combine all these metric perturbation functions, H0, H1 for the odd part, and the Q and A and capital H1, 0, and 2 for the even part, in a way so that we can have two different polarizations. But maybe this is related to the way that these waves, to see that, we would have to understand how this waves, right? How this QLM affects the space-time, right? But maybe there's a relation here. I think two polarizations is something that is universal for gravitational waves. Maybe I'm not quite sure. This is something that I'm still working on in my project for my master's. But great question. Yes, this is the question, right? This is the right on right where the trouble lies. So let me just for a second, I will try to find the seminar on YouTube, and I will try to put the link in the corrected slides for this lecture so that we can all appreciate the seminar. Okay, let me just bear with me, please don't leave. This is gonna be cool. Um, so okay, let me start sharing my screen again as soon as it loads. So if you are interested in going into this line of research, this is the kind of computations that you will have to do. Okay. Okay. Okay, so now what you are looking at right now is basically the notebook from Sage Math that I used to construct the metric perturbations, right? And get to the Reggie-Wheeler and Zerilli equations. Just one moment. Let me just rejoin the meeting from the other device. Okay. All right. Are you listening to this echo?
Only a bit.
Yeah, but I haven't I had it muted. But okay, now it's gone, right? Now I think it's gone. I think it's gone. Okay, so okay, here is the notebook. So let me just, is there a Zoom here somewhere? No, I don't think so. I don't think so. Okay, well, so here are the functions that I need to define. Nothing special. The Fourier transform functions, right? Because we want to deal with only the Fourier part. So here we define these spherical harmonics. Let me run all these. Let me run all cells here so that you can really appreciate it. And in the end, as you can see here, we obtain the potential for the even part, and the source SLM is the source term, is the source function for the for the even part. Okay. My computer is very old, so let's have some patience. But yeah, so let's see as it calculates. So only bear in mind also that I'm far from being very experienced in coding. So maybe this notebook could be very much shorter, right? But since I don't have the skills, I have to do it the hard way. Okay, so let me just get back here. So yeah, so here we define these spherical harmonics and some relations that they have. This is also some relations that I want to substitute maybe later to only to teach Sage to take the derivatives of these objects, right? Some identities as well. All right, let's go to the interesting parts. Okay, so here we start to construct the metric perturbations, right? So far here, all we did is construct the basis, right? We constructed the tensor harmonics, right? And now we're going to start to construct the metric, the background metric and the perturbations, right? So you see here is the Schwarzschild metric, right? Here's the Schwarzschild metric with and I use the notation with the ring here, just as we did in our lectures. Defined a derivative operator. This is this is the covariant derivative, taking the covariant derivative of the metric and equal to 0, just making sure that the metric is compatible, that the derivative operator, right, the covariant derivative is compatible with the metric, right? So this is the inverse Ricci tensor and scalars. We constructed them from the background metric. Here we constructed the metric on the two sphere, the gamma, right? And so here we're going to start constructing the vectors, right? The SA and SAB, right? Here we construct these vectors in such a way that now we are able to construct the axial perturbation, which is the even part, right? It's the even perturbation. The even perturbation, I'm sorry, this should be the odd. I think I wrote it wrong here. Yeah, yes, I'm sorry. This is the odd part. The axial perturbation is the odd perturbation part. This is confusing, even for me, that works with this for a couple of years already. So be careful. So okay, this is part of the what we did today. Remember that we constructed the matrix, and now all I need to do is to symmetrize, right? Apply this function which symmetrizes the metric in such a way that the components become this, right? So t theta is equal to theta t, and so on and so forth, right? If I wanted to show you let me see if I can show you the matrix form. So here it is. Here is the matrix form that after we symmetrize, right? We constructed this, symmetrized, and obtained the full odd metric perturbation in the Regge-Wheeler gauge, right? I'm working already in the Regge-Wheeler gauge in this notebook. So yeah, so the polar perturbation will be this matrix, right? We constructed term by term here, okay? But we could have done as easily as we did in the slides today, using the two-sphere metric, and so on and so forth. We need to symmetrize, right? And it is already symmetrized, but only to make sure, right, that it is a symmetric 0-2 tensor. We apply symmetrize here. We see the symmetry on the 0-1 indices, which are the first and second indices. No anti-symmetry, right? This is a symmetric tensor. So if we print them, we see that both are a field of symmetric bilinear forms in the sense that this is a 0-2 tensor. Both of them are 0-2 tensors in a four-dimensional Lorentzian manifold, right? Which I called RW, okay, for Regge-Wheeler. If I put both of them together, again, this is what the whole perturbation looks like, right? Which is basically summing the two matrices, right? To obtain the inverse perturbations, all you need to do is, well, raise the indices, right? And you do this with the inverse background metric, right? And we see, and we did construct this, it takes a little, and then we have the inverse perturbations, right? Here we have the inverse odd perturbation, which is a 2-0 tensor field, right? The inverse is a 2-0 because the original perturbation is a 0-2 tensor, right? And the same goes on here for the polar/even part, okay? Now we construct the source. We prepare the source so that we can, well, use the orthogonality relations the same way from the left-hand side and the right-hand side, right? So here are one part of them. We construct of them, and then here is the odd energy momentum tensor, right? Exactly the same as we did with the perturbation we do with the energy momentum tensor here, right? And then let me just check what this is. Oh, okay. Because the metric perturbation would not have any elements here because of the Regge-Wheeler gauge, right? But in terms of only for completeness, I added these terms to the energy momentum tensor because, you know, taking the derivatives and all that machinery could render some non-trivial terms. So just to make sure, I I created this here, right? These terms here, which will be the sources of the T equation, right? This will be the sources of the beta equations, right? The T0 and T1, right? And the Ts is the source for the T equation, right? Okay, so now here we are constructing the, I'm sorry, we're constructing the polar energy momentum tensor, right? Here is the polar energy momentum tensor, right? We are considering all of the possible elements, right? Here are the first quadrant, here are the second and third quadrants, and here are the fourth and last quadrant, okay? Symmetrizing this, hence we obtain, there's a cell hidden, why there's a cell hidden? Okay, so here is the full axial slash odd source, okay? Okay, and here is the full polar source, right? Right here. And putting them all together, the full source would look like this, right? Which is huge. Okay, this is why separating them is very useful and very helpful. So here, what I did here is only to, if I wanted at any time to see if my equations were comparable, were equal to those of Berti, of the Berti reference, I did some dictionary, I constructed a dictionary to translate the source terms that I constructed with the notation that Berti uses. Okay, and this is the inverse, right? To put back into my notation, the other function. Put into my notation back. So, okay, so let's building the Einstein perturbed equations. Now we start to build the axial equations, right? Which is basically constructing the first and second covariant derivatives of the perturbations. And see here that I'm plugging only the axial slash odd part, right? For the odd equations. So I'm doing this is all I'm doing. Constructed each term in such a way that this, so here I'm going to put them all together, right? Building the perturbed odd Ricci tensor, which is basically this. In the previous cells, we constructed this term and this term and this, right? Taking covariant derivatives of the axial perturbation. And then we constructed the Ricci tensor, right? Here are some spherical harmonics relations that I forgot to do, but now here. And here are the odd Einstein tensor, right? In this cell, we constructed them, okay? So here is the Einstein tensor. This is exactly translates what is here, right? This expression exactly translates this. So here we have the Ricci, perturbed Ricci tensor. The G ring here is a GS here, right? G invariant is here. The S is here, okay? The odd perturbation, inverse perturbation is here. In here, this term here, okay? And then I symmetrize this tensor, right? Just to make sure, run a symmetrized function. And you will see what we get, right? So if you check, this is the odd perturbation, right? Remember, the 0, 0 part of the 0, 0 part of the Einstein equation, of the Einstein tensor, the full Einstein tensor, was exclusively even. Remember, it was that matrix of A's multiplying Y, multiplying the spherical harmonic, the scalar spherical harmonic. So let's see what we get when we take the 0, 0 component of this tensor. 0, okay? Exactly as we wanted, because this is the odd part, right? This is the odd tensor, Einstein tensor. So since this the 0, 0, 0, 1 and 1, 1 are all even, all that we want is for them to be 0, right? Because they're all even, and this is the axial part. So okay, this appears to be working, right? But remember that when we went to get beta, had an index. The first index was connected to the first index. The first index of beta is the first index of the perturbed Einstein tensor. So if I want to know who beta 0 is, I need to take the 0 component here, but not 1, because this would be the first quadrant. I need to go to the second quadrant. So I need to do this, right? And look, this is exactly beta 0, right? This is here in this form because I didn't do the substitution to show that this is exactly S theta, right? So this expression for H0 would go in here also as well. But anyways, so yeah, this is exactly beta 0. If I do 0, 3, we still obtain beta 0, right? Here we have the same equation, right? It is the same equation if we put that term that was in the y inside the parentheses. But in 0, 3, you see that all that we have left in the 0, 3 after, because in here, in the substitutions here, I already applied the orthogonality relations, right? In such a way that the part that would be the components that would be multiplying the even spherical vector is not here, right? So this is the beta 0, right? The beta 0 equation, right? It is not really a grouped, right? This all of these are times H0. It seems a little longer than what we found, but we need to put some things in evidence here. We need to group some things here. But okay. And if I wanted beta 1, all I need to do is take this, and here it is, multiplying S phi as we expected, right? Let me just try. I don't know if it's gonna jam the computer. Let me just get back here to show you that we did this, right? Here. Remember? So this is beta, and these are the S's, right? The E to the O, the odd here is the S. So if I wanted to get beta 0, all I needed to do is set 0 here. And for each value of, independent of the value of A, here would be beta 0, right? And for delta G 03, I obtained exactly beta 0 S3, which is S phi. And for beta 1, I put this 1, 3, and I obtained beta 1, 3. Beta 1 times S3, which is S phi, right? Okay, so this goes on for a long time here because I need to do all these equations in a more. So here is one of them, right? 0, 3, right? So here is beta 0, right? Here is 1, 3. I take 1, 3 here. And here is beta 1, exactly in the form that we found, right? That we saw in the slides. And here I need to do some other operations here to put some operations here, some identities, so that Sage gives me the T equation. And here is the T equation, exactly as we found it in the slides, right? So here is the path to Reggie-Wheeler. So now we're going to do that we saw earlier, which is basically, well, we set this equal to A, which is beta 1. We thrown out beta 0 because it's redundant. And this is beta 0, beta 1, I'm sorry, equal to A. And then we do T equal to B, right? And then we isolate H0, take its first derivative with respect to R, which is basically going on here, and which is going on here. And then I substitute the expression for H0, H0 prime, and H0 into the first equation, right? And the right hand side, the left hand side, I'm sorry, the LHS here, the left hand side looks like this, right? And then what we did, we introduced the Reggie-Wheeler function Q, right? And what we did is exactly what I showed you. And then by doing the coordinate transformation, we end up with this, right? And here is the polar, I'm sorry, the odd potential, right? Then the same thing goes for the even part, right? So this is the part that you haven't seen, but which is exactly the same. So I plug in the Einstein equations in those first and second derivatives of the metric perturbation, only the polar part, and I construct them term by term. So here is the Einstein tensor, the polar Einstein tensor, right? Exactly as it is here. And then I need to obtain the equations, right? For K, H0, H1, and H2, right? So this here is one, which is basically the component TT, 0, 0, right? Of the polar part. And all the components that are significant, T and R, T phi, RR component, R theta component, and construct this all, okay? And then for the Zerilli equation, right, we set the source terms, right? Right here. This is the Zerilli equation, right? This is the Zerilli equation. The Zerilli equation, but this will transform into this side will transform into a wave equation, right? So there's a very convoluted sequence of steps that you must take. Solve one equation for the derivative of K, and then for the derivative of H1, and substitute them into one of the other equations so that we can get rid of some dependencies. Substituting these expressions, right? So that we can lose the dependencies on K and H0 and so on. And then, well, substituting the expressions and taking derivatives. This is a long and long and long. So we construct the Z. Z here is the Zerilli function, right? This is the analog of the Reggie-Wheeler function Q, right? Remember that Q was only a function of small caps H1, right? But here, it's impossible to get to only one variable, right? Since we started from 4, right? Which was H0, H1, H2, and K. But we reduced all this to an equation which depends only on 2 of them, right? K and H1. And these symbols here are some functions that we defined right here, right? Zeta and eta, right? Zeta and eta here. Okay. We construct this really function like this, the same way we constructed Q as H1 times F over R. And then, so here is this really, right? This is this really function right here. And this, what is multiplying K here is right here. What is multiplying H1 is right here, okay? Substituting then in the expressions so that we can find a differential equation for Z, right? So there's a long set of simplifications that we must do, and then voila. We end up with a Schrodinger-like equation for Z, right? For the even potential, right? And here the source, okay? And here, just so that you have an idea of the problem that we had with us, remember that the odd perturbation potential is this guy here. Let me just, right? This is the expression for the odd part. Now, take a look at the even part. Of course, there are a lot of terms here that are the same, multiplying things that we could at least group them, right? Simplify somehow. But yeah, and you could check that this by substituting F by 1 minus 2m over R and trying to simplify this yields the exact solutions given by Berti, given by Berti. Yes, given by Berti, because Valeria doesn't do this doesn't do this really with sources, right? So yeah, and this is the source term. This is the source term for this really equation, right? Which is effing huge, right? Enormous, gigantosaurus, right? But yeah, some of these things we can simplify, right? Some of the things we can't, because this is just the way that perturbations work. So let me just close this because we are done with this. Otherwise, my computer will crash. I have one last slide too. So yeah, so we went to the Sage Math notebook and saw how to do the same thing for this really master equation, right? And as seen in the Sage Math notebook, we obtained this equation here, which is this really equation, right? We saw how big was the even potential and the even source term, right? And this is the equation, the Schrodinger-like equation that governs the polar part of the perturbations, right? So here we end our journey. So we went on a journey that started in flat space-time, right? And this journey through flat space-time got us here, right? So we found out that, oh my God, I mean, a perturbation on the geometry of space-time, right, propagates, altering the geometry of space-time as it passes by. This is insane, right? So the geometry perturbation propagates as a wave, right? This is what this equation is telling us, right? So perturbation of the geometry of space-time propagates as a wave at the speed of light, right? We put the ansatz of the plane waves here in the wave equation and in the Lorentz gauge equation, and we saw that these are the equations it yields. So here, not only this wave propagates in the speed of light, but also, as well as electromagnetic waves, it only has uh, transverse polarizations, right? And then we took a turn and we went to curved spacetimes to take a look how this is going to play out in curved spacetimes, okay? And we discovered that in the context of perturbations in a spherically symmetric curved spacetime, the wave, this wave of geometry, this geometric wave is governed by Schrodinger-like equations with this look, right? And this is kind of amazing, right? Because the fundamental thing is here, because as this wave propagates through space-time, geometry is altered. Distances between points are altered. And this is exactly how they are able to detect it, right? With the interferometer, right? And here we end our journey together. Well, I thank you all. I thank you all the organizers. Victor, please, very much thank you and all the organizers for the invitation. This was an amazing opportunity for me. I hope that you guys at least were able to absorb a little. Perturbation theory is very tricky, and you deal with a lot of computations. It's very extensive computations. So don't worry. So don't worry if you didn't get all of the details, because this is supposed to be a first contact with the subject. So if any of you are interested in studying more of this, at least you already had a first encounter with the subject and will be a little less, I hope so, a little less intimidated by it. So extend my thanks to all the organizers, Victor. And that's it. I'm very fortunate to have been invited, and I'm very happy to be here. I'll be happy to be here again if you call me back. And that's it. That's it. Thank you all. Thank you all very much. Oh, and let me just answer a little some of the things that are on the chat, that I saw some comments that I wanna answer, but you can stop the recording, Victor, already.
All right, thank you, Vitor, for your lecture. It was a great lecture, and I hope we can meet with you again on next courses.
Well,